Good afternoon, everyone. Am I audible
Good
to you
afternoon,
all?
sir. Good afternoon, sir.
Good afternoon. Okay. So today I'll be playing the videos one after the other, and please go through the video a little bit seriously. Maybe we may not find time to complete the course uh, in our usual pace. I may be a little fast because your exams are fast approaching. Hardly we have 20 days of time in our hand, and within these 20 days, I have to complete a number of chapters. So, and moreover, I am something around. I am around the three-fourth of a chapter behind the other teachers. Maybe I will take some extra class if I require, but for the time being, we will go by our usual pace. But whatever videos I am playing in this practical class, please go through it a little bit seriously. Of course, everything will be covered in the class itself, but still then, please have a good, this will give you some good idea about what we are actually going to study, how we are going to derive the things. And as I told you, I will be out for vaccination. I'll start at 3 o'clock. At least I'll keep the video running till 3:30, and it will automatically end. So by 3:30, you people can leave the meeting, no problem. But it will continue even if I am not present. Secondly, I will play the video after 5 minutes. Let me have a break for 5 minutes because starting from 8 o'clock till now, I have continuously been taking the class, doing the examination duty, so I am feeling a little bit tired. I'll go and have a glass of water, use the toilet, then I will come and play the video. Please be online, and please go through the video a little bit seriously. No need of being too serious. All these things will be covered in the class, but go through it. Huh? And at the end of the entire semester, uh, before your exam, if you want, I can also share these videos with you all, no problem. But these videos are quite massive in their data, something around 1.5 GB, 1.6 GB, like this. So it is better you go through the videos right now. And if you are having any doubt, obviously I will not be present over here to clear your doubt altogether. So in the class on Monday, you can definitely ask me your doubt. Okay. So I will be playing the video within 5 minutes. Please be online. Similarly, we'll study about
students. This is my 14th video. Similarly, we'll study about magnetic field created because of a straight current carrying conductor, straight current carrying conductor. This is also covered in subchapter 28.3. We'll also talk about the magnetic field created by a circular current loop. So these are the things that we are going to cover in this upcoming chapter, number 28. Now the first thing that we will study over here is the magnetic field due to a moving charge. First we will cover magnetic field due to a moving charge. Okay. Now let us say there is a positive charge over here. Let us say it is Q, and let us say it is moving with a uniform velocity of v vector. Okay. Now suppose I want to evaluate what is the magnetic field due to this point charge Q at a point P over here. Let us say P over here, because in the class every time I have told you, if we want to evaluate the field, whether it is an electric field or a magnetic field, we must specify where we need to find that field. Now this point is a point of evaluation of the magnetic field. Sometimes this point is also known as your field point. Now let us say this field point is located at a distance vector of modulus r vector, or rather I will say if Q is located at the origin, then the position vector of this field point P is given by r vector. Okay. Now suppose I want to evaluate the magnetic field at this particular point because of this moving charge Q, which is moving along this direction at constant velocity v vector. Now let us say there is an angle which is made between your v vector towards your r vector, and that angle is phi. Now, obviously we have to take into account of this phi is of importance to us. Now let us say let the point P is equal to the field point where we want to evaluate. R vector is equal to the position vector of P with respect to Q, which is let us assume, which is assumed to be at origin. Now why we are taking it at the origin? Because this will ease our calculations, and we will see this is going to be a quite a easier way to evaluate the expression. Now let phi is equal to the angle between your v vector and your r vector directed from v vector towards your r vector. Okay. And lastly, v vector is equal to the velocity, or rather we can also say speed, whatever you want, because it is a constant speed in a particular direction. We can say velocity of the charge Q. Okay. Now actually there is no theoretical way or mathematical way by which we can evaluate this B. This B is actually evaluated by means of experimentation, and it was concluded that magnitude of B vector, that is equal to your B, is equal to or directly proportional to the magnitude of the charge Q, and it is inversely proportional to the square of the distance between the charge and the field point. So in this way we can write that B is directly proportional to Q by R square. Now if I want to replace this proportionality sign by a equal to sign, then obviously I can write it in this way. B is equal to a constant, and that constant I am writing it directly as mu naught by 4 pi q by r square. Now there is some additional terms associated with this particular expression, and that is V sine phi. Okay, so this is the expression for the magnitude of your P, that is your magnetic field, and equated at the point P, right? So over here, let me tell you one thing. Here, mu 0 or mu naught is known as the permeability of free space or vacuum free space. Now this naught indicates that it is free space. If there is no naught, then it is permeability of the medium. Now mu 0 has a mathematical value which is constant at 4 pi into 10 to the power minus 7 Weber per meter, per ampere meter. Okay, so if we'll write mu 0 by 4 pi, it is nothing we chapter that it is a vector quantity in some direction, and it can also be expressed in terms of a vector product, cross product. Now where is the cross product? Obviously mu 0 by 4 pi, they are constants. Q is a scalar quantity. V obviously is a vector quantity, and sin phi is a scalar quantity. So there is one absence of another vector quantity to which this V must be cross multiplied. The solution for this is very simple. Now B vector can be written as mu 0 modulus of Q by 4 pi r square. Let us write it down. V vector cross, just look over here, what I am writing, V vector cross A cap. What is A cap? A cap is the unit vector directed from Q to P. Okay, from Q to P. If this is the case, then obviously your A cap can be written as R vector by R vector modulus, because R vector is a position vector, and position vector by the modulus of position vector is going to give you the unit vector in the direction of R vector. So if we'll write this term and this term both are going to be the same, because when we are going to evaluate the magnitude part, we have to take the magnitude of V vector. So magnitude of V vector is V over here. Similarly, the magnitude of multiplied by sine of the angle, smaller angle between V vector and A cap. So this is simple, your vector calculations. So in other words, I can write, or in other way, I can write V vector is equal to mu 0 modulus of Q by 4 pi. Okay. Now this I can write. Now as I told you that your A cap is equal to R vector by R vector modulus. So over here I will write V vector cross R vector divided by, here there is a R square and here there is modulus of R vector. That is nothing but your R. So I can write it as RQ. Just see, this is the vector representation of the magnetic field produced because of a moving charge Q moving in a direction with a constant velocity of V vector at a point P, which is having a position vector of R vector with respect to this Q. So this is the expression. Next, we have to find the direction. Now, how to find the direction? Obviously, we have written like this, but now we have to understand how to find the direction. Now, in order to find the direction, let me have some modifications over here. Now, let us say I am having this one. Let us say I am having a plane. I am having a plane like this. At the end, I am having this point P. And let us say this is a plane. Let us say x-axis. Okay. So here also I can say this is my z-axis, this is my y-axis, and this is my x-axis. Okay. This is the origin, because I have told you here, I have told you that position vector of P with respect to Q, which is assumed to be at origin. So here let us say the Q was at the origin. Now over here, as we all know that this is a vector quantity and its direction will always be given by, or the direction is going to be in the direction which is perpendicular to the plane containing both V vector and R vector. Now, as you can see, your V vector is along, let us say, the XY plane, along the XY plane. So, V vector is in this plane, let us say. And your R vector is along the Z and Y plane. So, what is that plane which is going to be perpendicular to both of them? So here it is a little bit tricky. So this is going to be in this direction. So it is going to be in this direction. Okay. That means your B vector is going to be in this direction, because you see, if I draw a tangent over here, this tangent is perpendicular to this Z axis, and it is at this point, it is also now at this point, it is also perpendicular to your B vector. Okay. That means this B vector is going to be, suppose I will place my thumb in towards indicating your B vector, and I will curve my fingers, then the direction of the fingers is going to give the direction of the B vector. So in this case, here we can write that your B vector direction, or simply I can write direction of B vector can be determined by the curled fingers of right hand, where the thumb indicates thumb is along the direction of G vector. Okay. So in order to find the direction, what we have to do? We have to simply place the thumb of our right hand along the direction of B vector, and we will curl our fingers. The direction of the curl of our fingers will give the direction of your B vector. So it is as simple as that. Now, always remember that this is only for positive charge. Be clear about it. This is for positive charge. So for negative charge, just opposite of the curled finger, just opposite to the direction of curled fingers. As simple as this. Okay? It is as simple as this. So next, we'll move and study what is the magnetic field due to a current element. So we'll start. So this was 28.1, subchapter 28.1. So this was dealing with the magnetic field due to a moving charge. And we have derived the expression. Here, this is the magnitude part of the B vector, and this is the actual expression, vectorial representation. So this is the vectorial representation of your B vector, and B, this is equal to mu 0 q by 4 pi. I have already told you what is q mu naught and what is the value of mu naught by 4 pi. Again, V vector cross R vector by R cube. Now, this expression can be utilized to find the value of B vector. Also, we can use this principle to find the direction of B vector by using our right hand thumbs rule. So this is for positive charge, and for negative charge, it is just the opposite direction of your third finger. So this is what we studied just right now. Now, let us move to the sub 28.2 is going to deal with the magnetic field of a current element. I have already told you what is a current element. Current element is nothing but your I dl vector, and remember, current element is a vector quantity even though your I is a phasor quantity. Okay, so a phasor is multiplied with a vector quantity and this results in a vector quantity. So magnetic field due to a current element. Okay. Now we know that the magnitude of B vector, because in the last section we studied that the magnitude of B vector is equal to mu 0 q v sine phi by 4 pi r square. Now what is a current element? The current element is nothing but a part of the conductor which is carrying a current. Suppose let us say this one is equal to dl. This one is equal to dl, and let us say it is carrying a current I. Okay. So what is the magnetic field due to this current carrying element? Okay. So how to find it out? Now, in order to find it out, obviously I must specify where I want to find it out. Suppose let us say I want to evaluate it at the point P. Okay. So how to carry out all this thing? Now let us say this point of evaluation or the field point is located at with a position vector or R vector, considering this dl to be at the origin. Now I have already told you that dl, ds or dv can be considered as a point. Okay, because a very small length is nothing but a point. Similarly, a very small surface area is nothing but a point, and similarly a very small volume can also be considered as a point. So let us say this dl is located at the origin, and this point P where I want to evaluate the B vector is having a position vector of R vector with respect to this dl. Now how to find it out? Now we all know that in the last section we studied that your magnitude of B vector is given by mu 0 qv sine phi 4 pi r square. Now the total field created due to the current carrying conductor is the vector sum of the field created because of individual charges. Now when we are talking about individual charges, we can write this as B vector is equal to mu 0 by 4 pi r square q. Now in place of V, we will write Vt. Why Vt? Because when we are talking about individual charges, we know individual charges, they used to move at drift velocity. Now suppose I will write it as dp vector modulus. Now this is equal to, let us say, dp, and let us say this can, since it is a differential term, so over here we can write mu naught 4 pi r square. Now in place of q, we have to write dq, vd sine phi. Now why I have written only dq? Because this is a constant one, so we cannot change it. This is also constant, and this all are constant. So the only variable thing is your Q. So for if we are writing it as dB differential magnetic field, then this must be the differential charge. Again, we know that your dq modulus, now we'll write it as modulus, dq modulus is equal to, we have already studied it as N, that is the number of charge per unit volume multiplied with the volume. Volume is A into L. A into L. Now, here we have taken L as dl. So rather I will write it as dl. Okay? Into or multiplied with the charge of each particle, that is Q. So the above equation dB can be written as mu 0 by 4 pi. In place of dq, I will write it as N modulus of Q. Okay, I have missed out this modulus. Modulus of Q. Over here, let me write it as Vd. This in a bracket. Vd is finished. Next, we have this dl term. I'll write dl term over here. A sine pi. Okay, let me do one thing. Write down A first, then dl. Okay. Now, again, can you identify this term? This term is nothing but your J. And J, when it is multiplied with A, results in what? I. So ultimately, I can write this dB is equal to mu 0 by 4 pi. In place of N modulus Q Vd, I will write J, and J, there is a over here, J into A is equal to I. So I will write it as I. dl as usual remains over here, sine phi, I have missed out R square over here, divided by R square. Okay. Or this entire thing expression is going to give you the magnitude of the differential magnetic field at the point P due to a small current carrying element IDL. Okay. Now this particular equation is sometimes known as Biot-Savart law. Biot-Savart law. Okay. Bio, actually it is Biot. Spelling is Biot-Savart, but it is actually pronounced as Biot-Savart law. Okay. Now this is in magnitude part, but as we all know that in vectorial form, we have to represent this form. It can be written as dB vector. And dV vector over here will be written as mu 0 IDL vector. Now over here, I will do one thing. I will write A cap by 4 pi R square. Now A cap is the unit vector in the direction of this position vector R. So here A cap is equal to R vector divided by R vector modulus. So let us replace it. So dB vector is equal to mu 0 by 4 pi. I will keep it over here. dl vector cross R vector divided by R cube. Divided by R cube. Now this is again known as Biot-Savart law. So this was the magnitude. This is the entire vectorial representation of Biot-Savart law. But if we will take the entire length of this conductor, we were evaluating it, taking into consideration a very small differential length, but we will consider the entire length of this conductor and try to evaluate what is the magnetic field at the field point P. Then what we have to do? We have to integrate. So ultimately I can say P vector for the entire current carrying element will be given as mu 0 by 4 pi line integral IDL vector cross R vector by R cube. So this expression is going to give you the magnetic field due to a current carrying element or simply a current element. Expression for magnetic field due to a current element. What is current element? IDL vector. Expression for magnetic field due to a current element at a point P with position vector R vector with respect to DL. With respect to DL. Which is assumed to be at origin. Which is assumed to be at origin. So when we'll solve problems on this, everything will be clear. Okay. So we'll stop over here. Next, we'll make video for 28.3 onwards. Thank you. Okay, students. Today we'll study about the magnetic field due to a straight current carrying conductor. Let us say this is the axis. Let us say this is the z-axis, this is your x-axis, and this is your y-axis. Let us suppose say that there is a straight conductor which is lying along the y-axis like this. The length of this conductor is 2a. The one end is along the entire length of this conductor is along the y-axis. It starts from minus a along the y-axis and ends at a along the same y-axis. Now let us say this is carrying a current of I. Now we are interested to find what will be the magnetic field at a point P over here, which is located at a distance of x along the x-axis as shown over here. Now in order to find this, we have to take a very small length of this conductor. Let us say this small length is equal to dl, and see what is the magnetic field that is going to be produced because of this small current carrying element IDL at the field point P. Now let us say this is making an angle of, let us say, phi with respect to the positive y-axis, right? Now the position vector of this point P with respect to this DL, let us say, is equal to R vector. Now suppose let us say this small element, which is the source of the magnetic field at the point P over here, this small length is at a distance of y from the origin. Let us say it is at a distance of y from the origin. Now we have to evaluate what is the magnetic field because of this small element of this conductor, straight conductor carrying a current I at the point P over here. Once we could evaluate the magnetic field because of this dl, then if we will integrate it from minus a to plus a, then we can find the total magnetic field because of this straight current carrying conductor at the point P. Now we all know that your B vector is equal to mu 0 I by 4 pi line integral dl vector cross r vector by r cube. Now in this case, your dl, let us say this is your dl vector. Obviously your dl is a vector quantity, so dl vector over here is equal to dy a y cap, because I have told you that your length is a vector quantity. Now since this is along the y-axis, so I am writing it as dy, and the direction is along the y-axis, therefore I am writing a y cap. Similarly, r vector can be written as Now what is the coordinate of this point P? It is x comma 0. What is the coordinate of this DL? It is 0 comma y. Okay. Now you know how to find the value of r vector. This is this coordinate minus this, that is x a x cap 0 minus y, that is your minus y a y cap. Okay. Now, if I'll write r cube, that is the cube of the magnitude of r vector, then it is written as x square plus y square to the power half to the power 3. So in total, I can write it as 3 by 2, right? Now, with all these things, I will put it in this equation. Then what I am going to get? Before that, let me do one thing. Cross multiply dl vector with that of your r vector. So I will get